Okay, so today I'm going to talk about fairness-aware learning with distillation, augmentation, and robust optimization. And this is a joint work with my students, Sangwon Jung, Taeyeon Park, Dongkyu Lee, and also with collaborator Sang-hyuk Jeon at Naver AI. So here's the outline of this talk. So I'll briefly introduce myself and my research lab for a bit, and then I'll talk about some backgrounds in fairness-aware learning. I guess there has been some related talk in this summer school, but just to make common grounds to the audience, so I'll talk about some background, and then I'll talk about 3 of our recent work in distillation and augmentation and robust optimization at the context of fairness-aware learning. Okay. So again, as Professor Yu has introduced, I joined SNU ECE last year, and then I had a few work experience in industry and academia experience. For example, Sungkyunkwan University, Digist, Samsung, UC Berkeley, and Yahoo. So my research lab is called Mind Lab, Machine Intelligence and Data Science Lab, and currently we have 7 PhD, 4 master, and 6 BS students. And then 2 of our main research focus is on adaptive machine learning these days, which focus on continual self-supervised and unsupervised learning. And the second focus is the trustworthy machine learning, which mainly focus on explainable AI, fairness, and robustness. And today the topic, the focus is going to be this fairness in the context of trustworthy ML. So what is fairness-aware learning? So of course, the notion of fairness is coming from social science or law, right? So we don't want any favoritism toward an individual or a group. So this is kind of enforced by law in our society. But this fairness problem is also occurring a lot these days in AI and machine learning applications, because they're these days more and more making critical decisions that of which result will impact humans. So the fairness in machine learning is going to be also very important. One of the very popular example that we could see is from this Netflix drama called Coded Bias, kind of award-winning documentary. And this mainly talked about focus on the face recognition systems of many well-known companies like Microsoft or IBM, of which accuracy, for example, the gender classifier based on the face, of which accuracy is pretty high. But if you break down into different demographic groups, like darker skin color, male and female, then suddenly you can see that for some underrepresented groups, like female with darker skin colors, they have very low accuracy, right? So this is going to be the problem, right? And these fairness issues is not just coming in some esoteric applications, but it's really a pressing practical issue, right? So because these days, already there are many AI-assisted hiring systems, like AI interviews, and then AI. So and then you don't want these systems to discriminate between male or female, or AI is going to be is more and more getting applied to healthcare diagnostics, and of course you don't want the accuracy of these systems differ across different age groups, for example. Also, law enforcement, this AI system is already being deployed, and we don't want it to discriminate against race, for example. Right? So, from these motivations, there have been these days the research on fairness for machine learning has become very popular, and there have been several different notions of fairness that have been proposed. For example, first one is called group fairness, which essentially tries to make the statistical parity between different groups like race or gender, age. So for example, you want the accuracy of your system to match across all different groups, right? So that's the group fairness, and basically looks at some average performance. And another notion is called individual fairness, where the people with similar traits should be treated similarly, right? And so today I'll just focus on this group fairness, notion of group fairness. And then regarding this group fairness, again, people have proposed several different metrics to enforce or to measure or evaluate this group fairness, right? And one of the most popular metric is called equalized odds. Especially it's defined for binary classification systems. And mathematically it is defined like this, right? So let's say you have a predictor y hat, and then EO basically enforces the conditional independence of this prediction with the sensitive attribute or the group labels A given the ground truth label Y, right? So if you look at, oops, what? Sorry. Oh, okay, something is not right. So if you look at this expression, so in the red box, that's basically enforcing the true positive rate and false positive rates of a binary classifier to match across different group labels, A, right? And then we can extend this to multi-class and multi-group setting as well, which is given below, which essentially focuses on the accuracy of your system, and you want the difference among these accuracies among the different groups should be small, right? So that's the natural extension of the EO metric for multi-class classification. Okay, and then with these metrics defined and focus on group fairness, there have been several approaches to tackle this issue, and then these are typical fairness-aware learning approaches. First one is called pre-processing. So what this is doing is, basically this kind of fairness problem is occurring because there is some bias in the training data, across, that's relating the label and the group attributes. So the pre-processing approach first tries to remove any of the biases from the data and try to first learn fair representations. Sorry, this is a typo. Try to learn fair representations before training a model. So that's called pre-processing. And the in-processing approach is try to retrain a model because you know that there's a bias in the data and probably in the model. So you try to retrain a model with the fairness metric into account, right? So that's called in-processing. And post-processing is like after you learn, let's say your model is an unfair model or it has a bias, you try to pre-process this model to make this model more fair, right? So that's called post-processing. So today our interest is this in-processing method, and I'll talk about how we can approach or develop new methods in this in-processing approach. Okay, so a little bit more detail. So the in-processing method for group fairness can be typically formulated as given here. So the animation is not working as intended, but let me try. So typically in this formulation, we have the accuracy loss that's given in this red box, and then you add some fairness constraint as a regularizer, right? So that's given in this blue box. And typically these fairness constraints as a regularizer is given by using some kind of a surrogate function for the fairness metric that I mentioned, for example, the EO. Because directly employing the EO metric as a regularizer is not trivial. So typically people come up with some surrogate for this. Okay, but this approach, as you can see, is a regularized framework, regularization-based method. So because we have more objective here, if you train a model with this new objective, then typically it is known that there is something called accuracy and fairness trade-off, right? So if this axis is accuracy and this axis is fairness, this is the ideal point that we want to achieve, right? We want to have both high accuracy and good fairness. But then because of this regularization and regularization parameter lambda, there could be some trade-off between accuracy and fairness. So if you shoot for the accuracy, then you may sacrifice fairness. Or if you shoot for the fairness, then you may sacrifice accuracy. So our first work that I want to present is to maybe overcome some of this trade-off issue by using this framework of distillation. So the main question would be, can we use some kind of unfair teacher model for training a fair student model, and then we try to distill some predictive information from this teacher model so that we can achieve better accuracy and fairness trade-off. So I'll talk more about that. And then the second issue with this in-processing method is that typically all of the existing approaches or existing methods for this in-processing method, they require the group labels are fully annotated in the training data. So every training sample, you have the class label as well as the group labels. That's a requirement because people typically use those group labels to compute this fairness constraint in the regularization, right? So to that end, our second work that I want to present is, can we utilize this group unlabeled data to augment the existing training data for fairness and then improve the accuracy and fairness trade-off, right? So that's the second work that I want to talk. And then the third one is regarding this fairness constraint. Usually, again, as I said, people use some kind of surrogate for this fairness metric, not the exact the metric itself, right? Some approximation of the fairness metric like EO. Now, so in order to overcome that mismatch, we also tried to apply this robust optimization framework to exactly incorporate this fairness metric in the regularizer so that we can better optimize for that metric. Okay, so that's the third work that I want to talk about. Okay, so let's now go into each of this work a little bit more into the details. So the first work is called is about fair feature distillation, which was published in last year's CVPR. So the motivation is the following. So suppose we are given with the model, that has been trained on the training data, but it has resulted in some kind of an unfair or biased model. So let's say you are given with the face image, and then the model is trying to predict whether this person is attractive or unattractive. But then let's say it has been biased against the skin color. So let's say if you have some bright skin image comes in, then you tend to predict more attractive. Where you have some darker skin, then this model tend to predict more toward unattractive, right? So this is the typical phenomena that we observe if the data has some kind of bias, right? But obviously we don't want this kind of bias in your model, right? Because you don't want to just predict the attractiveness based on the skin color. So the typical in-processing or retraining method, again, as I showed in the previous slides, put in some kind of fairness constraint as regularization term, and then retrain the model, right? But then it will result in some accuracy drop because then there will be some trade-off between accuracy and fairness. Right. So then our question is, can we utilize this existing unfair model to prevent this accuracy drop, right? And if you think about that question, it resembles with the question that this very popular knowledge distillation or KD method is doing. So what they're doing is in the typical KD is you utilize this teacher model. When you're training a smaller student model, you want to distill some knowledge from the teacher so that the smaller student model can also achieve high accuracy, right? But of course, the existing KD methods, they don't care about the fairness, right? They only care about the accuracy. So our question is, can we devise the fairness-aware distillation method? Right. So the main idea is, again through this example, maybe this original biased unfair model, it is biased maybe toward the skin color, but it may be also using some kind of group unbiased useful feature. Let's say like some facial features like this, right? So suppose the teacher model have learned both of these features, right? Some group unbiased, some group biased, right? And maybe we can only distill this group unbiased feature from the teacher when you're training the fair student model. Then probably you can achieve both the fairness and also high accuracy, right? Now, so again, if you're new to this area, you may think, okay, why is there a trade-off between accuracy and fairness? I mean, you can think of a very dumb model that always predicts with the same label. Then it's perfectly fair, right? Because you're depending on the different groups, you're always giving the same prediction. But obviously, this will have very low accuracy, right? So we want to achieve both good accuracy and fairness, right? So our main proposal was to use the MMD, maximum mean discrepancy based MMD function, and use that as a regularizer or the distillation method, right? So our loss function will look something like this. So again, our goal is to train this fair student model with parameter theta, right? We're not only using, of course, it will have this accuracy term for loss function, but then we will also have this additional regularization term, which involves a teacher model, right? So let's say we have another teacher model, biased, unfair teacher model, and then we compute the distance between the feature distribution of this teacher model and the student model. Now, what are these? So this one is the feature distribution of class Y, the distribution of the features that has same class label Y. So that's this PTY. And then PSAY is that the feature distribution of the student model for the same class label Y and the group label A. And we want this distance to be small by putting this as the regularization term. And this is the empirical MMD loss, right? So basically, essentially what this is doing is like, okay, for all the feature distribution of the student model with the same class label Y across different group labels A, we want all of them to be close to the feature distribution of the teacher with the same class label Y, right? So that's this regularization term. And right, so this is the what I just said. And then from this, we can see that this, this method we call MFD, it can, by using that regularization term involving this unfair teacher, it can simultaneously have two effects. One is to assimilate the feature distribution from the teacher model to the feature distribution to the student model. That's exactly the knowledge distillation, typical knowledge distillation is doing. And then because the second one is we want the feature distribution of the student models for specific group A and Y always get close to the teacher distribution of class label Y. So probably it will reduce the distance among these PSAY for all A. And this is the fairness constraint effect, right? And regarding that, we are able to show two small lemmas with this distance metric. So first one is, again, knowledge distillation. This regularization term, we can show that this is an upper bound of the distance between the feature distribution of the teacher and the student. And this is really the knowledge distillation effect. And then the fairness is like, this regularization term upper bounds the feature distribution between different groups, right? So you want the distribution across different groups to cluster together. Right? So with this method, we have experimented on several data sets. First one is the synthetic data set called CFAR10S, right, where we artificially made some bias in the data. Namely, this color or grayscale is the group label. CFAR10 has 10 classes. So first 5 classes, we made it biased toward the grayscale images, because we made the training data like 80% of them as grayscale and 20% of them as color. And then the latter 5 classes, we made it reverse. So 80% would be color, and then 20% would be grayscale. Now, if you train with this naively with this data, then by looking at the color or grayscale, you may bias toward first 5 classes or the latter 5 classes, right? But at the test set, we made the balanced test images for both color and grayscale images. So we try to measure the accuracy and fairness on that test set. The real world data set involved these 2 sets, UTK face and CELEB A. UTK face is a multi-class classification and multiple groups. And then CELEB A had 2 binary classification with binary group, right? So UTK face, the group is the race, target is the age, and CELEB A, the group is gender, and the target is the attractiveness or not, right? And then we compare with the baselines that just naively do typical knowledge distillation like Hinton's KD or FitNet. Second one is that just retrains with the fairness constraint, like without using the teacher model. And then the third is just the one that naively combines this above 2. To just you retrain, basically have 2 regularization terms, right? You retrain with the fairness constraint, and then there's a knowledge distillation term. And this is the result. A lot of numbers, but then if we so here CIFAR 10S, UTK face, and CELEB A, and then this is the teacher model's accuracy and fairness metric. Accuracy higher the better, fairness lower the better, because it means the small discrepancy. And we can see from this summary table that our MFD compared to the teacher model, which just naively trains with cross entropy without any fairness constraint, you can improve both accuracy and fairness because we utilize this predictive information from the teacher model. I mean, you can improve sometimes, right? The accuracy, and also the fairness is significantly improved, right? So this is some positive result. And then this is some analysis result saying that, okay, so all of the animations are not working. But so this for CIFAR 10S, this purple box is what I just showed, right? So the horizontal axis shows the skewness of the color and grayscale for the CIFAR 10S. And then this dotted line is the accuracy of the scratch, the unfair teacher model. And red square is the student model that you achieve. So right? And then the blue is the fairness metric. So this triangle, if you look at this, so this is the accuracy of the teacher model and the fairness of the teacher model. If you use this MFD, the accuracy improves. The accuracy improves, and then the fairness dramatically improves as well. And then what are other points here? It's like if your teacher model is even more skewed toward the color, and then still use that as a distillation model from the teacher, you still get at least some improvement of the student model. So, which means that even if your teacher model is really, really biased and unfair, but has some high accuracy, you can still distillate some predictive information from that model, such that your student model will achieve higher accuracy, but at the same time always achieving very good fairness. Okay, and then if we also visualize the feature distribution, the unfair teacher model, it's quite predictive across different classes, but also if you visualize the group, you can see that there are some discrepancies. It's like the feature distribution from different groups are also different, whereas in MFD, the class labels are very discriminative. The features are very discriminative for the class label, but for the group label, it more or less overlaps. So there's not much difference in that distribution. Okay, so now, how many times do I have? How much? 5 minutes, okay. Okay, so yeah, so I'll have to quickly go over to the next topics. So the second one is about the augmentation or partially annotated group labels, right? So the motivation is the following. So again, existing in-processing methods, they require fully annotated group labels, as I said. Even in MFD, in order to compute this term, we need to know the group label for every training samples in your data, right? But collecting this group label for all the samples can be impractical, right? Because humans have to annotate all of the, not only the class label, but also the group labels. And collecting this personal information is sometimes protected by law, so you cannot really get these group labels. And also sometimes they have to get expired, right? And here, so to that end, we consider the setting where, okay, what if we only have partially annotated group label data, right? So suppose you have some part of the data here. Let's say you have both target class label and group labels, but then some part of the data you only have target label and you don't have the group label. So this is the practical setting that we can think of. And we proposed this confidence-based group label assignment, or CGL method, to kind of fill in this group labels and then utilize that for training. So the main idea is to, okay, you first split this group labeled data to train and validation, and then obtain a group classifier and find a threshold for the confidence level. And based on that threshold, you apply this group classifier to this group unlabeled data, and then try to predict what's the group label. And then from the threshold that we get here, so the letters are all broken, but this is a tau. So if the confidence is larger than tau, then we believe this group classifier. And if it's lower than tau, then we randomize this group label. That's the way we try to fill in this group label. And then with that filled in group labels, we just apply ordinary schemes that we like. So it can be combined with any schemes. So the simple baseline would be, okay, without having this threshold, just believe the prediction of the group classifier, or just randomly label these unlabeled data based on the population estimate for each class label, right? And then we show that, okay, putting this appropriate threshold to believe this group classifier is helpful. That's what we show in these two propositions. And then, our experimental result shows that if so horizontal axis here is the group label ratio. So let's say you have only 10% of the data, original data, with group labels, and 90% are not labeled, not group labeled. Then any of the existing methods, for example here, you have to use only 10% of the data to come up with this fairness aware classifier, right? So because then you're also discarding 90% of the class label, the accuracy will drop significantly, and then the fairness will also suffer because you only have 10% of the data as information. But if you apply CGL, we can show that, okay, our accuracy, because we are using all the class labels, so accuracy is maintained, and fairness is also significantly improved. So that's what we show here. And also we can show the similar thing for other data set as well. And the important point that I want to mention with this work is that, okay, using this CGL, we can actually augment the existing training data, right? So, the UTK face, the data set that I mentioned, has both target class labels and group labels for about 20,000 images. But then there may be other data set which has the same class labels, but not with the group labels. So group unlabeled data, but only the class labels. And these kind of data, for example, the fair face, is much easier to obtain than UTK face because you don't have to label the groups, right? Applying CGL to this combined data set, UTK face plus fair face, and then kind of fill in the estimate of the group labels. In this table, we show that this MFD, the method that I just mentioned, plus CGL can achieve the state-of-the-art accuracy and also the fairness, right, compared to this MFD here. So this result here is the one that I showed in the first part of this talk. But we can even improve this by just augmenting with the data set that only has the class labels, right? So notice that, okay, the accuracy improvement, you can get it, but then fairness also improves. Okay, so maybe remaining couple minutes, I just want to talk about this the very recent work called class-wise group DRO. So to recap on the in-processing method, right? So the regularization-based method was like that, and then I mentioned that typically these regularization terms were the surrogate of the fairness metric. So even in MFT, we used MMD distance between the feature distributions, but that doesn't really exactly correspond to the fairness metric that we care, right? Like EO. And these methods are very sensitive to model architectures. Another class of in-processing method is called rebating-based methods. And it's mainly heuristics. What they do is you try to reweight the losses for different groups, A, based on the number of samples or the loss values and so on. So you try to enlarge the weight for the underrepresented groups and kind of make the weight smaller for the majority groups. But these are mainly heuristic, and there's no theoretical guarantees for these methods. And then the motivation of this work is, okay, can we use the exact fairness metric as a regularizer? And also, can we make a principal connection between this regularization-based and reweighting-based methods? And also, can we make an efficient iterative optimization method? And we can say yes to all these questions. And we were able to use this so-called distributionally robust optimization framework for achieving this. Okay, so DRO is a very popular topic. So ERM is the typical method that we use to try to minimize the average loss while training. DRO is trying to minimize the worst case loss for certain distribution set. So PI is a distribution over the data set, data samples in this case. And then there's something called group DRO, where you look at different groups and then you optimize for the worst case loss for those groups, right? And then here, the uncertainty set is the simplex over all different groups and labels. And then people show that if you solve this, then when there's a distribution mismatch from the training and the test set, then this could be very robust for that kind of setting, right? Now in our work, we try to propose a class-wise group DRO that basically applied group DRO for each class Y separately, right? And then also design this uncertainty set for this distribution for the groups as this chi-square divergence-based ball, like this. So I think the details I have to skip. And then we apply some iterative updates for obtaining this data. So our lemma, we're able to show that if we use the 0-1 loss, and if you try to solve this class-wise group DRO, this inner maximization term, we can show that this is equivalent to the empirical loss plus some variance term on the group losses, right? And then the next proposition, we were able to show that this variance term is actually equivalent to this fairness metric that we typically care, the difference between EO or accuracy, up to some positive constant. Right? So then from this, we can show that, okay, if we solve this class-wise group DRO, then we are actually employing the exact fairness constraint as a regularizer. And then also we can devise this iterative update schemes for this data, the model parameter, and then Q, which is a weight for different groups. And the solution of this Q is basically the reweights for each group. And these are just emerging based on solving the optimization problem, okay? And then again, if you apply this method to different data set, we were able to achieve better accuracy fairness trade-off as you can see in this blue dots, right? So this is good fairness and good accuracy for variously different kind of data sets like tabular, vision, or NLP data set. And then we are also able to visualize this weight, the reweights that we we get by solving this optimization. And the detail that I didn't mention is that this Q can also have negative values. So we show that, okay, by having this, by penalizing some high accuracy group severely, we can make the accuracy between different groups very close. Whereas if you just train the model by scratch, the accuracy will diverge like this. Okay, so that's some analysis figure. Okay, so sorry, I had to rush for the third part. So let me just summarize. So initially, we came up with some distillation-based method as a new regularization-based in-processing method using MFD. Second, we were able to augment the group unlabeled data to improve both accuracy and fairness. And then we applied the robust optimization methods to have exact fairness metric as a regularization function and also principal rebating scheme. Okay, so that will conclude the talk. Thank you very much.